Good evening all, welcome back to programming on the C64 in BASIC. This time we are going on to, chapter 8, making sound and music. Alright, let's just turn it a little bit. Okay. Now I'm terribly sorry that this took so long to come out. Just things have just been piling up and conspiring against me. It's just that I've never been in a good mood to do things. I've been trying to think of a good way of doing this video and I just couldn't think of a good way. So I thought, I'll just go do what like I did in the first one, just read the manual and see what we get up with. Come up with. And about things conspiring to get against me, Audacity decided to die just before I recorded. So now I'm recording this through OBS. And so the audio quality may not be the same as usual in my videos. Alright. So, first things first. Let's have a look at down here. Okay. So, let's start reading, shall we? Making sound, the SID chip, sample sound program, playing a song. Now, before I go any further, I do have to say I have read through this, kind of. I glanced through it, and this is going to be a lot longer than I would have liked to, because there's a lot of text in here. And there is Chapter 9, Advanced Data Handling, which we might look at, but they're all pretty much common, basic things. It's just arrays and whatnot. So we'll see. If you want to know about how to do arrays in BASIC, and especially Commodore BASIC, then yeah. So basically, this might be a two-part video like sprites. I don't know. I haven't planned this out at all. So, let's start off with, we've got the SID chip. Oh, hang on a minute. Sorry, we'll go up a little bit further. Up on top, this one. Your Commodore 64 computer is equipped with one of the most sophisticated electronics music synthesizers available on any computer. Which was true at the time. This chapter is an introduction to using your computer's sound chip, the SID chip. The main features that the SID chip provides are volume control, multiple voices, waveform, frequency, envelope generator, attack, delay, sustain, and release. The SID chip, or sound interface device, contains 29 8-bit registers, numbered 0 to 28. Each of which is responsible for a certain component of sound generation. In this chapter you will only be concerned with the first 25 registers. These are stored between locations 5527-2 or 5429-6 inclusively. Here's a summary of the SID chip map. So I'm going to do what I did with the sprites and I'm going to write this out. So, alright. But for this we're going to need, we're not going to use LeGimp this time, we are going to use MyPaint. So, let's have a look. First things first. Okay, so, what we got? Registers 0 to 6 equals voice 1, 7 to 13 equals voice 2. Essentially channel to, not channels really, instruments. How about we do that? 14 to 20 equals voice 3. And then we have the ones that we probably won't be looking at so far, but we've got 21 equals the low frequency. So that 22 equals the high. Yeah, that. And 24 equals volume and filters. Okay, so there's our registers. Like with the sprites, we just put some data into these registers here, and we get something on the other end, is my guess. So hold on, I'll come back to the set Commodore. We don't need to see my beautiful mug right now, do we? Nah. So let's see. Before we go on to discuss how sounds are generated, type the following program and run it. This will demonstrate just a little of what may be achieved by the SID chip. Example program 1. Alright, I'm just going to have to show you something for a tick. This little example is that many lines, that from about up top here all the way down to here. So, sorry, but I think I'm going to be typing for a while. So, start. So, the starting register, so starting memory address is 54272. So of course S equals 54272. Okay, so let's get back into this. So let's go. So 5 S. I'll still an OBS that. Oh, I thought I. Ooh, almost thought I. Yeah. We all okay? Okay. All right. I don't know what happened there, but okay, because on my Linux setup I have focus following the mouse, and I was still focused on OBS rather than the Commodore 64. Anyway, let's start typing. So 5 equals. It's been a while since I've done this. Sorry it did take so long. 5 S equals, so the start of the SID chip, so which is 54272. Okay. 10. 4. L equals S2 S plus 24. Poke. Oops. Gotta remember it's all capital letters regardless. Hang on, I'm gonna move this over a little bit because this mic is getting in the way. Hold on. Hopefully that wasn't too noisy or hurt your ears too much. And I'm going to be a little bit more louder because now I'm closer to the mic, because now I can type properly. Sorry. There we go. Had to move it over because of the pen and tablet. So let's get back to what we were doing. So hang on, I even missed S2 S plus, whoop, that's right, plus 24. Jesus, I'm getting a bit. Oh, I'm getting a little bit rusty. L dot 0. Next. So this just clears the sound chip. So it clears all the memory and whatever's in there. So 20. Poke. S plus 5,9. Poke. S plus 6, 0. So that's adding something to it. So that's adding a waveform to it. So this looks like it's adding. Oh, I did make a bloody mistake, didn't I? S plus 5,9. So it's putting a 9 in the 5th register. I wonder what that register is for. S. I'll sure you'll say soon which one's which. Hang on a minute down here. Oh, okay. Never mind. I can see it further down. So 6 minus 0. Alright, so I'm sorry about this watching me type everything again. It's like I said, I've just been away from this for a fair while, so I am a little bit rusty. So this just sets the maximum volume level, and if you're wondering why I know this, it's because it says right here in the code. Remark set maximum volume level. Okay. So now, read some of the data. What data? So read. Whoop. Still haven't understood how this reading still works. HF, LF, DR. If 50. If HF, sorry about the dog, there's nothing I can do about it. If HF is then 0, then not that. Oh, I got my English mixed up there. And my coding. Oh no, I've got my English and my coding. 60. Poke S plus 1 HF. Poke S LF. And I did it again. God damn it, I've got to stop pushing shift. It's driving me nuts. Where am I? HF. Poke S with LF. Oh, so high frequency, low frequency. Okay, I see now. So 70. This should produce some sounds by the end. So poke S plus 4, 33. So we're putting in the fourth register, we're putting the control register? We're putting 33 in a control register? Okay. 80 4 T equals 1 2 DR. Next. Because is anyone actually catching this? I'm not so sure. Poke S plus 4 32. So we're putting 32 in the control register. 4 T equals 1 2 50. Next. So that's adding a little bit of delay, that little for loop. And for fuck me, I forgot my line numbers. That's annoying. Poke S plus 432 4 T equals 1 2 50. Next. Go to, did it again, 100, so go to 40. So basically what's going, so after all this is just all data, so don't worry. So where's 40? There it is. I fucked things up. Anyway, so let's, so just do, hang on now. I'll just do it down here. I missed something. So I'll go read HF LF DR. So it looks like it's going to read. Okay, so it's when it does the read, it reads the first one, second one, third one, second one. So it reads it in groups of 3s. There's data down below. I understand now, I think. So that's right now. Okay, good. So 110. This bit is the tedious bit. So data. What? Data. I do miss doing this though. I should have done these videos a lot earlier, and I'm very, very sorry about it. It's just a lot of things have been happening, that's all. And I just have not felt up to the challenge of doing it. Yes, I have done other videos, but I don't know, I just wanted this one to be nice and good, and I don't know, I just didn't feel like I was up to doing it at that point. And there's been several times when I've been working on, go home, do it. Go home, do it. And after work, get home and I don't do it. I just didn't feel like doing it. Yeah, well, you know, this shit happens. You have your ruts, you have your high times, you have your low times. I'll take that road, you take the low road, and I'll get to Scotland before you. Speaking of which, I was reading a really nice Scottish tale the other day. It was real nice. Which may confound a few people, me being a full-blooded male and all. But it was actually a nice little love story. It was quite nice, actually. So what is it? Well, we're up to 140, so 32. Yep, okay. Lost my place there for a tick. I'm not going to tell you what it was and all that because I might get yelled at. So no, I won't. But I did like it. It was a really nice, touching tale. Taking place just after the First World War in Scotland. Up in the Scotland Highlands. That was nice. I'm not even typing properly. 214 250. Well, one good thing, I got a message today and I got my tax back. I'm going to get my tax, yay! I'm not going to be owing anything, I don't think. 63 250 160 data 19 63 250. Geez, my zero's getting a bit worn out there. That's 260 250. Which one am I doing? 160. 19 63 250. Okay, I see what's going on here. So it reads the first number, which is 2525, into, which is HF, which is into 1. So high frequency value, so the top of the waveform, essentially. Then it sets the control. Oh no, then it pokes S. Okay, so then it does the low frequency one, which is 0. Oh, okay, I see. So it's in groups of 3. So we're going dee doo dee doo dee doo dee doo by the looks of it. Okay, cool. So consider each 3 numbers in this data to be that note at that point. The values that define the note on voice 1. So 21 154 63 24 Okay, yeah, I lost my place there. So 63 and 63. Yep, that's it. And why can't a full-blown male man not like a good love story? If it's a nice, touching one, that's good. It's not sappy or anything, it's quite nice. Yes, of course a lot of men won't admit to it, but yeah, we all do like a good story. 63 250, and I think these ones turn it all off. So that looks like we got our data. So let's list it just to make doubly certain of it. Okay, so 54270, yeah, S2S24 poke. So that clears it all out. Yep, okay, cool. Oh, stuff it, let's just run it. Let's see what we get. And hopefully this isn't too loud on New Year's. And 70. Ah, I missed a poke. God damn it, poke. And probably a lot of people are yelling at me right now because let's face it, I'm looking at the book here and looking at my keyboard. I'm not looking at this, not looking at the screen. All right. 33. Okay, let's see. And list it just to make certain of it all. Yep, got me pokes, got me pokes, got me pokes. So DR, I think that is the delay register. So DR, where's DR been used in any way, shape? Oh, hang on, no, that's the hold. So that's how long. So this is how long it's, how many cycles it's holding the note for. So this is the high. This is the low frequency of the note. This is the high frequency of the note. Oh no, high frequency of the note, low frequency of the note, and then how long, how many cycles to hold it for. Seems easy enough. Let's run it. And I hope this doesn't hurt. Ah, now what are we? I'm missing a T. Ah! The joys of debugging and whatnot. So 90. Poke. S plus 4. 32. 4. T equals 1, 2, 50. I suppose me liking good love stories. It's because I grew up with two sisters. I always watching sappy movies and almost have rubbed off on me. Anyway. List. Let's make absolutely doubly sure of it this time. Yay! I think that's working. Alright, run it. Okay. Why'd it stop? Why'd it stop? Yeah, next. It should have looped, but it didn't. So let's run that again. Huh. So let's go to, oh, hang on a minute. High frequencies. Oh, hang on. I got an idea. These are the control values. So you see here, if high frequency is lower than that, then end the program. Oh, it's not gonna repeat itself. It's gonna run out of memory. Oh, that's what that does. So this 40, this repeat is just to go next 3, next 3, next 3, next 3, next 3, next 3. Okay, I see now. So let's run that again. So we get a nice little. All right, so let's read the book again, shall we? So, line 5 stores the start location of the SID chip in S. All other registers are accessed by simply adding their number to S. Fair enough. Volume control. Your Commodore 64 has 16 volume levels, numbered 0 to off to 15 maximum volume. Register 24 on the SID chip controls the volume level. To set the volume, you simply poke the value you want into the register. Line 30 in the example program sets the maximum volume level to 15. So that's the maximum volume we're getting out of it. You would normally only set the volume at the beginning of your program. Note that the volume level determines the output of all three channels of your 64's voices. Okay, so let's read some more. Voices. Your Commodore 64 has 3 voices, which may be played separately or simultaneously. The register map for each voice is shown below. So, okay. So let's go back to, hold on, let's go back to the GIMP for a tick. It's not the GIMP, it's bloody my paint. So basically what we got in here, let's just look in this here. So I'm just going to talk about this one, alright? So, the first one, so basically each of these voices has 6 controls in them. The first one is the low frequency values, which is basically the low frequency value of this voice. 1 is the high frequency value. 2 is the pulse width. It's a low pulse width. And 3 is the high pulse width. 4 is the control register. 5 is the attack and decay settings. And 6 is the sustain and release settings. So basically each voice has low frequency, high frequency, low pulse, high pulse, control, attack, decay, and sustain and release. Okay, so let's bring that back down again and go back onto this. So let's turn the page, shall we? Sound like I'm an old children's record. Turn the page. Okay, frequency. Sound is created by the movement of air. Think of throwing a stone into a pool and seeing the waves radiate outward. When similar waves are created in air, we hear a sound. Every sound produced on your 64 is made up of a high and low frequency value. Each of the 3 voices has 2 registers in which the frequency values are stored. The 2 values in each voice are combined to form the frequency value in 16-bit form. The chart below showing the memory locations of each voice's high and low frequency registers is shown below. So hold on, I'll show you this little table. See? Hopefully you got a read of that. There we go. And for good measure, hold on. Please ignore the wine spot. And there's the other one, that registers I was just talking about, just so you know. Okay? Alright. Let's go back to the Commodore. Alright. I really wish OBS had a big red light or something saying I'm recording. Because all I got now is just a stop recording thing. I'll just say, is it a stop or not? Anyway. To play a musical note or sound, you must poke the sound's high frequency value into the high frequency location of the voice you want, and poke the note's low frequency value into the voice's low frequency location. Line 60 in the example program. So, okay, sorry. I'll take a few more breaths. Okay, hang on. I'll list out this program again. Sorry, so I can all read along. And while I'm reading, you can read the program and see where we go. Okay. In line 60 in the example program, pokes the high and low frequencies from the data statements into registers 1 and 0 respectively. This sets the frequency for voice 1. To create a frequency other than those listed in the note table using what's this? To create a frequency other than those listed in the note table, use the following formula. F equals, hold on, I'll use my paint. Hold on. Okay, let's move this over a little bit, shall we? Okay. So what do we got? We want, so it's, hang on, am I the right way around? Yes, I'm the right way around. Okay, so it is, over here. So it is frequency equals F Y out divided by 0.06097, where F, okay, so where that is the frequency you require. So if you know what frequency you want, just divide the frequency you want by that, and you'll get the frequency you need to add into your program. To create the high and low frequency values for the note, you must first make f into an integer, i.e. delete any numbers to the right of the decimal point. Now use this formula to calculate the high frequency location. So, okay, let's do this again. High. Hang on, I'll just make doubly certain that I'm actually... Okay, cool, I was just worried that I wasn't actually showing you the MyPack thing. Anyway. So it is. So we go high. Equals. And so integer or whole number is f, so this f by 2, 5, 6. Now it gets you to your high frequency. Now what this actual little formula means is calculate this first, right? This will always produce a decimal point, so I've got point, alright? What this does, it transforms that, so 2, 3, transforms this number here into just 1. So it gets rid of all that. That's what this integer thing means, cast it as a whole number. For the low frequency, equals. So if I'm already making it into a nib, why do I need to do it? Oh, probably because of this one. So low, your low frequency for the note. Yeah, and the following formula gives you the low frequency location. So F. So your frequency, your calculated frequency that you did here, minus 256. So times it by your high frequency. Okay. So first you calculate that, then that, then that. Okay, that's weird. Not quite sure I understand that, but okay. OBS, where are you? Okay, so let's put this back down. That one. There we go. A little bit lost there for a second. Okay. Then to obtain the note, simply poke the value of low into the low frequency register and the value of high into the high frequency register of the voice you wish to output the sound. Now here's something even more interesting. We got waveforms. The type of waveform you select determines the timbre or quality of the sound produced. There are 4 types of waveforms. Triangle, this waveform contains few harmonics and a mellow flute-like sound. The shape of a triangle wave looks something like this. Okay, hold on. See? And I'll just go back again. The next one, Sawtooth. This waveform contains all the harmonics. It is a bright, brassy quality. Here's what the Sawtooth sound looks like. So, there we go. It's basically what I drew in the last video that I did of this crap. Of the SID chip. I was doing some demonstrations there of what it can do. Okay, and I bet you what we got on the next page. The pulse. So variable pulse wave. This waveform contains variable rectangular pulse. Start again. Variable pulse wave. This waveform contains variable rectangular waves. Changing the pulse width makes sounds ranging from a bright, hollow noise to a nasal, reedy pulse. Here's what it looks like. Okay, this one. That is the pulse. So square wave, which is what most chips produced at the time. including the NES. And yes, I am comparing a computer to a console because there was no difference back then. There was literally nothing. White noise. This waveform is used mainly for sound effects, e.g. explosions, gunshots, and surf, and ranges from a low rumbling to hissing. It looks like this. Well, what do you expect a noise wave to look like that? Okay. So, the waveform of each voice is held in 3 control registers. These are numbered 4, 11, and 18. The component parts of each control register for each voice is as follows. Oh. Oh, okay. So, hold on. Go back to here. So, let's have a look. Oh, where's my program? Back. I swear it was putting 33 or something in the control register. Which is the control register, yeah. And he was putting 33 in there. So it was this bit here, the control register. So he's basically defining what waveform it is. So if I was tempted, 33. Component parts of each control register can be voice. For each follow is as follows. 0 is a gate. 1 to 3 are unused. 4 triangle waveform. 5 sawtooth waveform. 6 pulse waveform. 7 noise waveform. The gate bit controls the envelope generator. When this bit is set to 1, it triggers the envelope generator and the attack, decay, sustain cycle begins. When the bit is reset to 0, the release cycle begins. Setting bits 4, 5, and 6 to 1 selects that particular waveform. Line 7 in the program says the output for the sound for voice 1 using a sawtooth waveform. This line also sets the gate bit. You can set a combination of these bits, i.e. pulse and sawtooth, but this will produce pretty weird sounds. So you can't combine all your waveforms in one, which is weird, as it says here. Anyway, so let's try something. A sawtooth. Let's change that from a sawtooth to a pulse. No, pulse won't work. How about noise? So if we change this to, say, I don't know, let's say noise, so two more, which is 5. Let's see what we get. I hope this works. We'll see. So let's run it, see what we get. Didn't do anything. Why did that not do anything? I don't understand. I think I do. I think I do. Hold on. I'm going to have to get this out again. Sorry. But I'm going to have to do something really quick. So let's go. We got 1, 2, 4. Hang on a minute. No. Scratch that. We've got 1, 2, 3, 4, 5, 6, and 7. Right. So what we got here, what the original one was, it was a sawtooth. So 5, and this one, the gate, which turns it on. That doesn't make any sense either. Oh, hang on a minute. So this one is 1, this one is 2, this one is 4, this one is 8, 16. That doesn't make any sense either. doesn't make any sense. 16, 32. Oh, hang on a minute. It's this one it was on. You idiot. 32 and 64. So if I was to make this to be noise, I'd have to make it this to be... Oh, sorry. Hold on. So this is what I was just doing. I was sorry I wasn't showing you. I was just basically working out the binary numbers. So basically, what that 33 was doing was this 32 plus 1. Because we're looking at the positions. Hold on. I'll show you what I'm looking at. I know you're probably a little bit confused right now, but I just worked it out. So basically here, up the top here, this is how you control your waveforms. This is what the control register was for. So basically, hold on if it focuses. It was on a Sawtooth, which is number 5. I was right. Oh no, hang on. 0 index. My bad. So 0, 1, 2, 3, 4, 5. Yeah, okay. So if I was to change this from there to 4, so I needed 1 there, so I need 16, so 17. If I change that to 17, it will change it to, hold on, I'll go back. Let's go to this. So if I changed it to this one and 1, that will make it a triangle wave. Let's try that, actually. Let's try that. I think we finally worked it out. So if I make this 17, enter. Now let's run it. I can type run it. I know I can type run anyway. I just don't like it because it looks ugly. I was right. It changed it. It changed the waveform. So let's try again. What's the next one we can do? Sorry. So I have changed it. I'll just do a printout. Sorry. I'm getting ahead of myself here. I'm going all over the goddamn shop. I'll move OBS over here so I can see what's going on. Okay. We'll move it over this side. Okay. So this up here. This bit 17 here. That now changed it to a triangle wave. So it's setting it into the control bit, which is the control register, which sets the waveform. It's weird. Why are they using terms like that? I don't know. Anyway, put 17 into there, and we get ourselves a triangle. So I wonder, what if we change that to 6? So we need two. So hard to write with the mouse. So that's a duck. Okay. I got all my indices out of whack. So let's see. To put it on noise, I'm going to need 128. So 129. If I change that to 129, I should hear some noise. 1, 2. Whoops. 1, 2, 9. Let's hear some noise, I should say. Just run. Ah, god damn it. Run. Let's change that to 1. Let's try that to 128. So it doesn't like stop. Got 128. And we go down here. Let's try run again. That way it doesn't immediately attack. Let's see if it holds a note. Nope, that don't work. Let's try our pulse wave. So we need 65 for that one. Okay, 65. And run. It won't work because the frequency high and low, it doesn't work with pulse waves very well. Because we're not setting a pulse width or anything like that. That is pretty cool. I understand it now. So let's put this back to 33. And that is cool. Very good. Very, very good. Alright. So let's see. Hang on a minute. I'm going to try some weird noises. Like I said, not to do. So let's put some noise in. So let's go 128 plus 32. So 33 plus 128. So 33 plus 128. Let's see what we get. Well, I tried something. It doesn't work. Let me try it. Okay, let's move on. Let's do this one more time. Alright, so let's move on to the next bit. Okay, the envelope generator. The volume of a musical note changes with the from the moment you first hear it until it dies out and you can't hear it anymore. When a note is first struck, it rises from a zero volume to its peak volume. The rate at which this happens is called the attack. And then it falls from the peak to a mid-range volume level. The rate at which this occurs is called the decay. The mid-range volume is called the sustain level. When a note stops playing it falls from the sustain level to zero volume. The rate at which it falls to the rate it falls is called the release. The following is an illustration of the four phases of a note. So I'll show you this little diagram down here. So it goes up when it's struck, goes back down, and holds it for a little bit, then drops it. There we go. Put you back over here. Alright. Note, attack, decay, and release are rates. Sustain is a level. Each of the cycles above gives certain qualities and restrictions to the shape or envelope of a sound. These bounds are collectively called parameters. The attack, decay, sustain, release parameters are collectively called Adsr. There are two registers used for the Adsr parameters for each of the three voices. These are 5 and 6 for voice 1, 12 and 13 for voice 2, 19 and 20 for voice 3. The attack and decay parameters share the first of each pair of registers, 5, 12, 19, while the sustain and release parameters use registers 6, 13, and 20. So let's go back a little bit for a tick. Go back to the bases. Back to our registers for each voice. Right, okay. Okay. So let's look at our program. Let's see what we can get. Hold on. What am I doing? Go down here. List, because we're losing bits of it. Okay. So DR is high frequency, low frequency. Doesn't look like it's doing it, actually. No. Doesn't look like there's much. Oh, hang on a minute. 6. Oh, okay. So, what's it adding the sustain at? It is 6. Okay. So, up the top here, sorry, this one here, number 5 is the attack and decay. So, it's putting 9 into the attack decay settings of voice 1. And this is putting 0 in the sustain release settings. So it doesn't hold it for very long. So if I was to change that to say, I don't know, say 3. Say, let's go for scale, go 5. How about that? Now if I run that, okay, so it's kind of holding it a little bit longer, but let's get our settings a bit better first. So go back to where I was. Okay, I understand now. Oh my god, there's a lot of crap here. Okay, whew, alright. These pairings are used because the settings only require 4 bits or half a byte. The amount of storage is called a nibble. Okay. The first 4 bits of a byte are called the high nibble, and the last 4 bits are called the low nibble. The attack settings for the 3 voices are stored in the high nibbles of registers 5, 12, and 19, while the decay settings are stored in the low nibbles of these registers. The sustain settings for the 3 voices use the high nibbles in registers 6, 13, and 20, while release settings use the low nibbles in the same registers. Before poking any value into Adsr register, you must first combine the high and low nibbles by adding them together. For example, the attack rates occupy 2 to the power of 7. So let's go over here to my paint. So 2 to the power of 7. Blah, blah. So I think this one. Yeah, this one. No, hang on. This one? No. No, this one. Yeah, this one. Then go away. Don't need you. So this one holds, occupies, so the attack rate occupies that one, this one, and this one. So that's the attack. So basically how fast it rises up to volume. 5 and 4. I was right. It occupies this one. 8 can stay. So 8 to 4. So the values are 128, 64, 32, and 16. So if I move this up a bit, I used the wrong value. It's plus 6 to, let's try 1, 2, 8. And let's go down here and let's run it. So that did change it. Okay, cool. 16. Decay rates use 2 to the 3, which is that one, I think. 2 to the 2, 2 to the 1, and 2 to the 0. Okay, I've mixed this up immensely, okay? I think I know what I've done wrong. Rubber. Where's my razor? Go away. Not working. Anyway, go back to you. Don't paint now? No. I'll turn that off then. Okay, cool. So there should be a 0 here. Anyway, because they all start from 0. So let's get rid of all this. So we go 0, 1, 2, 3, 4, 5, and 6, and 7. So these 4 are the attack. So if you set that up, you got that as attack. And then you got these 4 bits here, which is the decay. And as we learned from our binary up here, you just got to add these values of decay. So I think I set myself a very, oh hang on, I know what I've done here with the 128. I set very high attack, but 0 decay, so it just goes down. Okay. Alright. Bits or, okay, so it's 128, 64, 32, or 16. So 128 to 8. 64. I've messed this up again, but I am not in the mood. So 32. Like I said, this was a long time ago. I've always said my binary maths are not all that crack. Can't to be. So these ones are either. So these are 8. If I can draw an 8 with a mouse, that'd be nice. 4, 2, and 1. Right. Okay, I was right in the first one. Alright, enough. I'm getting all over the place. So, what happened initially, 128, so this was just 0. So if I put an 8 on the end of that, which is, so I'll go 8, 128 plus 8. So plus 8, which should give it a long time delay. 8. So let's run this. So it'll be very long attack and very high decay. See, it holds itself for longer. That's great. That's cool. Alright, so we're getting somewhere. Okay, suppose you want set high attack value of 12. High attack value 12 and low attack value 2. Easy way to combine the two rates is to multiply the attack value by 16 and add it to the decay value. In this example, the resulting value is 194, i.e. 12 times 16 plus 2. You can use this formula whenever you wish to combine two values, range from 0 to 15, into a high-low nibble format. Line 20 example program sets the attack decay rate to 0 and attack and 9 decay. Okay, that's okay. So it's the attack rate decay to 0 attack and 9 decay. So it goes right up. The maximum attack rate is achieved by using a multiple of 15 and multiplying it by 16. You can increase the decay rate by adding together all the decay values, which is the maximum decay rate, which is 16. So if I put this as 16, let's see what we get. I'm getting a little bit confused. Are you? Okay, so yeah. Alright, so I got tick. Okay. Here are some sample attack decay pokes. Okay, so if we put in 66, let's see what we got with 66. It's supposed to be medium attack and delay, so let's try this. And run. Not bad. So let's max them out. So 255 will max out both. Oh, goddamn, I'm still looking at this. Okay, sorry. Let's look at this. So, let's max this out. So, 255. Run. My God, that is just staying there. Oh my God. That is really just staying there. Alright. Okay, we just clicked over the 1 hour mark, so we've got a little example program here to run that shows us the attack and whatnot. So I'm just going to go new and just clear out the memory, because this one requires a whole new program. It's not that big, don't worry about it. Can I clear the screen? Never mind. I think it's... There we go. Thank you. Alright, so 10 4 equals 4 L equals this one. Program's written really, really weird. 5 4 2 7 2 2. This one is no spacing whatsoever. I mean, seriously, look. Have a look at this thing. Okay, it is a programmer's worst nightmare. Look at this. There's no spacing whatsoever in that program. Ugh. That's a big bad no-no. Always space out your bloody keywords. Alright. So let's go back. Okay. 10, 4, 2, 5, 4, 2, 9, 6. Yep. So poke. L. 0. Next. This just clears out the SID chip. That's all it does, it's just clearing out the memory. 20. Poke. 5 4. 2 9. 6 1 5. So this sets the maximum volume. Fair enough. 30. Poke 5 4 2 7 7 64. What's this one do? Sets attack and delay. Okay. 40. Poke 5 4 2 7 3 and 1 6 2. Poke 5 4 2 7 2 37. This is just giving it a note. So these are the high and low frequencies. So that's, yep, that's a high. 273 is the high. 272 is the low. So here we go. 50. Print. Press OK. OK. 60. This is new. What's this? Get K $. Oh, okay. So it gets the variable of whatever you've hit. If K equals oh, what was that? Equals nothing, then then check the keyboard again. Okay. 70. Poke. 2 7 6 17 4 T equals 1 2 200. Next. What's going on here? So, oh, God damn it. You're not spacing things out. 5 4 2 7 6 17 4 T equals 1 2 200. Next. Yep, I got that right. Pretty sure I got that right. So this one is set triangle waveform. Okay, 80. Poke. 54276. 16, so that turns it off and does a nice little delay for t equals 1 to 50. Next. Okay, and 90 go to 50. Okay, so let's list this all up. Should be okay. Press that key, so let's run it. 80. There's a syntax error. Oh, FO. God damn it. Alright. 40. I know it says Ford, but it should work. Okay. So if we go list, let's change that like it says here in the book. Let's change it to 190. Which is line, what is it? Line 30. So if we change this to 190. And now run. Oh yeah. Okay, that's getting really annoying. Okay, so with that, I think I'm going to have to call it a night on this video, because I'm going to be here for another few more pages, actually, by the looks of it. We've got another program to come up. We've got a whole crap load of stuff here. Well, like, see, look, we've got all this. Oh, hold on. When it gets, close you down, sorry. So we can read it better. Okay. So we just wrote that program there. Now we got all that to go through. All that to go through. All that to go through. And now all that to go through. All that to go through. All that one to go through. Oh, gee, dusty. Sorry about that. And all that to go through, and that's it. So we might be able to get through this on the next video. But until then, hope you enjoyed this little bit here. We learnt a little bit of the SID chip. We figured out how the data is done and all this. I don't know how to do the music and whatnot, but hey, we'll see what we do. Oh dear. Got actual doll crying. Oh jeez, I remember doing that one. Oh, fuck me. Alright. I think I'm actually missing a few pages. 98, 29. No, I'm not. Okay. In any case, hope you enjoyed this little one. Wasn't much in it. Sorry. I was a bit back and forward. I know. I just went ahead with this. I'm sorry it took so. And once again, I am so very sorry this took so long to come out. I am so incredibly sorry. Anyway, I hope you enjoyed this video and hope to see you in the next one. And please start coding this. If you are coding this, please send me videos of what you're doing. Just take a little screen grab of your emulator and just send me a link in the description down below and I'll see what we can do. I'm sure many people can make as many cool things in this. I'll be happy as Larry if you can. So please, thank you for everything you've done. And thank you for being so patient with me. And it's just been enormous. So I'm just going to do something here. And 10. Oh, go to 10. Right. And with that, I thank you all, and I'll see you all next time. Bye bye.